Firstly, you all know all this, and just at the end of this, you'll think that the National Measurement System is totally addicted to this substance. The only difference is that we are migrating the CO2 out of the container. What is it? CO2 is a waste product with a value, and we've got a big value for it. It's a very simple fluid. Some will argue with the figures, but we'll come back to them later. It's not an easy product to deal with, although it seems very simple. We've got to ensure fair and equitable trade for the product, safe operation of transportation, efficient operation, and we've got to meet the regulators. And in my talk, I'm going to concentrate more on everything above the ground and above the sea, from the process, production, through to the storage. We've got our legislation in place, and as it was said earlier, 1.5%. You might not think that's terribly challenging, but when you look at the measurement of this difficult fluid, that is difficult. We're going to struggle. The variability of the carbon price is going to be a big driver on how we design our systems and how it's going to be implemented and whether we can afford to have them at all. And obviously we've got to show the integrity of the whole system right through. You all should have that engraved in the inside of your foreheads before you even start listening to a talk in CO2. So put it there and remember it. But in terms of CO2, that is where we're going to be working generally when things go well. What are the issues? A custody transfer measurement system for CO2. Simplistic system, basically a producer transporting to a disposal site. Where are we going to measure? Probably the person producing the CO2 wants to get rid of it as quickly as possible. So he wants to pass the liability on at his gate. So we want to measure that CO2 into the pipeline. We may have other inputs, all of which are going to have to be measured into that pipeline from clusters from different owners of CO2 or producers. We might have a change of operation where it maybe enters a sea line or a transfer between different pipeline operators. Receipt at the platform, and finally, injection to the wells. And notice the plural. We don't just stick it generally down into one piece of pipe under the ground. This may be transporting out to a network of wells here, which may have different owners or different strata, potentially in the future. I've missed out the export to other sources on the route of the pipeline. They would also need metered. Who's going to be responsible for the ownership of this? The pipeline operator doesn't want to own it. He wants to just be a lorry driver, load it into the back of his truck, ship it to the other end and dump it. He doesn't want to take liability. How do we reconcile the differences across the system? We've got all these measuring points. They will not agree. These metering systems, we'll be lucky if we get them to agree to 0.5%. How are we going to reconcile these losses? Or maybe even gain. You might find your pipeline is generating CO2 if you've got your measurement systems right. Who owns the CO2 when it's delivered to the store? Where do we transfer this liability? Is the delivery point going to be on the platform or each individual well? Or the seabed? If it's the seabed, I think you can forget most of the schemes. The cost of installing and maintaining 1.5% accurate meters on the seabed will probably stop most injection schemes dead. Multiple wells, multiple owners, and how are you going to distribute this stuff subsea? Will we be allowed to use allocation metering techniques where we use a primary measurement and allocate it through lower accuracy meters across different owners? Will that be allowed in the regulation? I'm not sure. Why does it matter? You'll all argue with the figures exactly, but basically what I'm telling you here, there's a lot of money in here. And that's going to have to be paid for somehow, as well as meeting the regulatory demands. And we've got to work out who carries this financial risk based on the measurements that we are going to be taking, and which measurements are finally going to be used in this process. And can we allow more than one measurement system to contribute? Or how do we allocate between two measurement systems which, again, will not agree? Where else will we measure? In the process. We haven't picked up much interest from the industry at the moment, from serious innovation on measurement within the process. It must be there, but we haven't picked up on that. How do we allow for venting if you've got to repair a pipeline? Are you going to measure it out, or are you just going to do it by inventory calculation? Leakage and dispersion has been talked about all day, so I'm not going there. In well and in strata, again, I'm going to leave that for another day in my talk. It's dealt with well elsewhere. We're going to have to do flow measurement in this system. We're going to have to get uncertainty in mass, and the regulators have been good for a change. They've dealt with mass and not volume. Thank goodness. Some common sense in the physics of this. Custody transfer, transfer of ownership, costs, value, and regulatory compliance. All slightly different drivers, but we've all got to try and fit in there. We're going to have to get the process right. How are we going to control the process of injection into a well if you start to back pressure and everything else have to cut down and flow through into a well? Most meter types will demand regular calibration to meet regulatory requirements, and there are currently no laboratories in the world running CO2 calibration facilities for the size of meters we're talking about. They don't exist, and they're very expensive to set up. There is also no recognised primary standards for the measurement of CO2 and the calibration of flow meters. They don't exist, and they're going to be very difficult to design and build. One for the regulators. When you've been looking at the regulation, the Measurements Instrument Directive could impinge on our choice of flow meters if it's imposed. Some of the big schemes that are around just now are proposing to use the primary device, a meter which is not covered by the Measurement Instrument Directive and not approved, so may not suddenly be allowed. Something to think about, and we can talk about that elsewhere. CO2 is metered for EOR around the world, but not regulatory. It's not stringent. There's experience, but not at these levels. So, little in technology. We can use differential pressure meters, volumetric type meters, or mass meters. What have we got? Differential pressure meters. Orifice plates. Widely used. They should achieve the 1.5% uncertainty. There are two-phase flow issues if we ever get into that regime, but they can be used there, but they can be damaged by two-phase flow by slugs coming down. They've got a limited turn-down ratio. They will not have a huge rangeability. A Venturi will struggle to make the 1.5%, in fact probably won't, but there are subsea versions out there in existence, so it's a potential technology for down well, but you'll not make your 1.5%. Cone meters, similar to Venturi in accuracy, not a lot of information out there. There's no doubt that they will work, but again, they will need calibrated. Orifice plates don't need calibrated in flow. They do need taken out for regular measurement. Volumetric meters, turbines, expensive. They will require calibration. They're not well characterised for CO2, especially liquid CO2 where the viscosity is incredibly low. We don't know an awful lot about how they'll behave there, and they'll definitely not work assuming a water calibration. Vortex meters, great for process control, won't touch the regulatory requirements. Ultrasonic. There isn't a good proved meter yet. They'll come. They're on their way. But basically, CO2 attenuates the speed of sound, attenuates the sound signal. We're not getting a clean signal through the CO2 as yet. But it's coming. These meters will give us the largest turn-down ratio in big sizes, but they will probably require recalibration, and there isn't anywhere to do that, unless we find a mechanism and a guideline on how to deal with that. Coriolis, quite a large pressure drop, especially in gas flow. Limited in pipe diameter. It will probably survive a blowdown situation in an accident if a pipeline has to vent through it. It will measure gas, it will measure liquid, probably measure through into the dense phase. Doesn't like two-phase. They will need regular calibration. Steady state single-phase flow in CO2. It's solvable. We will get there. It's just a case of time, setting down the regulations and the guidelines. I've got no concern that we will get there with some work, some investment, and some studies on how these meters behave. Issue is how we're going to deal with the rangeability in the flow on your metering station. If your power station is ramping up and down through the year, your other inputs from a cluster are switching on and off. Have you built a metering station that will cover the rangeability of the CO2 coming into the pipeline? We'll probably need a manifold of a number of meters in parallel. Will we need check or standby meters, as are common in hydrocarbon accounting for fiscal measurement? I don't know. We will have limitations if we're working in the dense phase. What are the limitations? Survivability if the phase changes in the pipeline. When you're blowing down, a leak, a burst, anything like that, your meter might not survive. I can accept that they're not going to work. That's okay. Density is a big issue. No matter what we're doing, we're going to have to understand what the density of the fluid is at the meter. It's sensitive to temperature, it's sensitive to pressure, and it will be sensitive to composition. If it's a volumetric meter, like an ultrasonic, we've got to know the density to the same level of accuracy, if not better. If it's an orifice plate, we get away with the square root of the density, which is a good selling point. That's why CO2 density slope with temperature is quite steep. And if you start working in here, it's very steep. Gas we can probably cope with, but liquid CO2, we've got issues in defining the density accurately enough at the flowing conditions. Moving on. Composition. There's a typical chart of composition that might appear in our pipelines. How are we going to do it? Are we going to sample and take the sample off into some kind of analyzer and look for these products in there? Do we have to do that online, live, and pick up all these things? Or can we put it in a bottle and send it to the lab? Can we analyse using sensors in the pipe for components and composition and concentration of components? There's lots of analyzers out there. Most are geared up to measure at atmospheric conditions. Our pipelines might be running in liquid at 150 bar. How can we get the sample representative without flashing off hydrogen first and getting a badly representative sample into our analyzer? None of these that we know of have been validated at process conditions. Why? We're going to have entry spec conditions into our pipeline to avoid corrosion, to avoid safety, and to stay away from phase boundaries in the transported liquid or fluid. What happens if a producer starts producing CO2 with a contaminant? At what point do we have to shut that out? And what happens and the financial cost if that producer is shut out for a period of time due to a faulty sensor? The financial and safety concerns are very, very significant in restarting the whole process again from a stop. Bad specifications and not picking it up could cause a significant safety risk on your pipeline if we move into two-phase flow unexpectedly. Takes us on to this, predicting the physical properties. Okay, we've got our composition, but what does it mean? We know what CO2 is. There's umpteen good scientific papers. We've pinned down the properties of pure CO2 extremely well. But what we don't have is a good consensus of mixture models when you put contaminants in. There's probably too many researchers working on it at the moment and not communicating. There's no focused building of models backed up by good experimental data from academia. The experiments are slow, they're long-term, and they're time-consuming. So we need to do something about thinking of sharing that knowledge and getting that modelling from composition checked against experiment. We need good economic properties of fluids and equations of state models to fit into control computers and flow computers that will run actively from the output of your samplers. You need the best models for trading and analysis so that you know how much CO2 is in there. We need to standardise these equations of state as early as possible so that when people start writing contract agreements now, we are using common equations of state and not run into the situation that the LNG people have of having 4 or 5 equations of state being used across the trading world. Not good. We sample, we analyse, we calculate the properties, we calculate the density online. We've got to measure our density for our volume, from our volume to our mass. We've got to avoid the phase boundary effects of having contaminants in there. If we don't know this, we have to put compression costs up. Or, in the gas pipeline, you've got to bring the pressure down, which reduces your mass transfer. It's costs. The big danger if you fall outside the envelope. There it is again. There's our model. There's our picture. What happens if we add contaminants? There's the phase boundary line, the original. Add contaminants. Phase boundary moves up, but you also open up 2 phase regions in here. But suddenly at 20 degrees C, your compression at 60 bar has to go up to nearly 100 bar to ensure you don't fall into a 2-phase region in your pipeline. That's cost on your pipeline. That pressure's got to be kept well up to avoid it. Same picture again, but these are the operating regions that we believe will probably have to be required to give safe operation and economic operation of pipelines. Allowing this to come down by better measurement would reduce compression costs. Allowing this to come up a bit might allow you better mass transfer through your pipeline. What our aim is an integrated measurement control system, combining all these elements, your flow measurement, your calculators, your equations of state, your sampling, and your sensors that are actually measuring the compositions. And these have to be combined in some way. Leak detection and measurement, we've got to do it. How we do it, I don't know. It's still to be addressed. There's lots of techniques. We've talked about some today. Optical techniques across areas. Fibre optics strung along the pipeline and detect a temperature change if there's a rupture. There's lots of things. We've got to deal with the monitoring of the geological. I'm not going to go there. Relax. And we've got done a lot of dispersion modelling in the industry. We've still got issues over the measurements and the sensors used in dispersion modelling techniques. So I'm going to leave all that for another day. So our main conclusions, we've got limited learning from what's out there on the EOR and the CCS pilots on the actual measurements. It's a new technology, new challenges, large numbers of measurement issues, and we need these phase diagrams, equations of state, sampling, and new inline sensors for the properties. We've got to get this dependency in the modelling right. Our flow meters, we don't have many choices out there on what we're going to use, and we're going to watch that they fall within the regulation, within the directives, and our usability. We're going to need stable, accurate density, or else we're wide open to large financial exposure. Designing the metering systems has to be tied very closely to the projected use of the pipeline or the transport system. So we've got to investigate all this, evaluate the current state of the art and devices, evaluate sensors and mixtures of sensors, and experimental determination. Evaluate CO2 screenings, geological monitoring. We've done all that. What are we doing, and what have we been doing? Well, National Measurement Office, and for your interest, National Measurement Office are the government body who sponsor the work at NPL, NEL through the measurement programs. So they set the strategy, provide the funding. They recognised CCS a number of years ago and commissioned a series of studies, and we've delivered them over the last 3 years. That's us. Our salespeople would never let me go without showing something about us, but you can read it in the stand. What we've done is much more important. We did a review, 2009, of measurement issues. Possibly needs revisited, but it's not far off what I've given today. This hasn't been published yet, but the work is completed, basically looking at some physical properties research work, and that's been carried out around the country in various researchers, and we commissioned some as well. We've got this one published, Research and Development Needs in CCS, and we are currently developing some test facilities for specific aspects of measurement within the CCS to support CCS. 3 items on the agenda are working towards at the moment. We've got a flow loop working 6-inch gaseous CO2 up to 20 bar. It was commissioned and running last week with 3 flow meters in the line. They all gave readings, and we're busy looking to see if they agreed with each other within some level of accuracy. But the real work will start in July, where we've got a client putting a number of flow meters in the loop for comparison purposes. But limited, 20 bar, but it is a starter. Getting us our gas flow measurement and an ability to get a handle on that. We're building a composition and sensor test rig. And this is a small rig designed gas and liquid, 150 bar, where we can test samplers, extraction into that, install sensors, and look at their behaviour with known mixtures. So we'll put known mixtures in, compare them. The third rig, which jumped ahead, is one which is going to explore two-phase flow and the onset of two-phase flow in mixtures, in small pipelines, as a research study. It won't work on full-scale metering or items. So that's a research activity rather than a full things. We also run our club and have been for 3 years. Seminars. 6th one is coming up in Edinburgh on 13th of June, and you're all very welcome to go to John Morgan at the back there, and we'll see if you can get an invite to that. Commercially, we're launching a joint industry project looking at all of this. We've got 1 company signed up and 6 looking for budget approvals at the moment to sign up. They've got expressions of interest. And we've got 1 rather wide-ranging commercial job undergoing at the moment. It's confidential for now, but the client wishes it to be public domain at the end. So that's good news for us all. Okay, and the rest of it is what we're available to do on a more commercial basis on studies, exploration of any design or anything else. And this is going backwards, which is a good trick. There we go. And there we are. Okay, finished.